This is my Chump final breadboard prototype. Chump is a 4-bit computer capable of manipulating, reading, writing, and storing data within RAM in a 16-line program. Here is Feinberg's program running. This program reads from address X, loads it into the accumulator, stores it back to address X, then repeats. In the top left corner is my addition to this project, where every instruction is printed out in letters. The Chump begins at the PC. The program counter outputs a binary count from 0 to a maximum of 16. Essentially, the program counter tells the Chump where it is in the program. Next comes the program ROM. The program ROM is a programmable chip that essentially determines the Chump program's overall purpose. It chooses which instructions will occur at which lines of the program. This means that the user must manually program the chip using an EEPROM programmer to choose which program will be executed. The PC output is connected directly to the program ROM's address inputs. The program ROM output contains 8 bits. The first 4 bits is the operation code, which connects directly to the control ROM address inputs. Essentially, it calls out which instruction should be done, as every instruction has been given a predetermined address that was coded into the control ROM. One thing to note is that every single instruction needs some integer to go with it. For example, if you were to load value x into the accumulator, you would need value x to be paired in sync with that instruction. As you can see, there are 2 types for every instruction, constant and it. This represents the way you can retrieve the number to be paired with such instruction. Constant means the value is taken from the lower nibble of the program ROM output, and it means it's taken from RAM. How this is done will be explained later on. Within the circuit itself, the MUX, or multiplexer, is used to determine whether a memory value or a constant value will be used, where the A inputs connect to constant and the B inputs connect to memory. When the select pin is high, a memory output will be used, and when select is low, a constant output will be used. The output from the MUX is connected to 3 places: the ALU B input, the PC, and the address register. The output of the ALU is connected to the accumulator. The accumulator is an 8-bit register that holds the ALU output so that if needed again, it can be used in the next instruction. The accumulator output goes to 2 places. The first is the ALU A input. Let's say you want to keep adding 1 to an initial 5, you'd need to have the accumulator output feed back into the A input of the ALU to continuously add 1. The function you would use would be A plus B, as the 1 comes from the output of the MUX, which would be a constant. But first, on the first clock cycle, 5 would be loaded into the accumulator. On the next cycle, the value of the accumulator would flow into input A, a 1 would be added, and it would go back into the accumulator. The other place the accumulator output goes to is RAM. This would be used if you want to write some data to a certain address in RAM. The RAM has 2 4-bit inputs and 1 4-bit output. The RAM output is connected to the MUX B input, and this is how memory functions are used, as the value of x comes from RAM. Now I'll show Feinberg's program from a circuit diagram perspective. On the top left is Feinberg's entire program. On the top right is the program ROM output for the current instruction, and in the bottom right is the control ROM output for the current instruction. Let's say the address we want to write and store to is address 2. We have to program the program ROM to ensure that. So using our predetermined control ROM code, we know that the read constant address is 1000. So the first line of the program ROM will be 10000010, since the constant is 2. Once all the lines in the program ROM have been coded, we can move on to the simulation. The first instruction is read 2. Importantly, 2 will move to the address register, where it will be held for the next instruction. It will technically flow through the ALU, where the function is simply B, but since the accumulator bit is high and the accumulator is actively low, this value will not go into the accumulator. On the next instruction, load it, the value 2, stored in the address register, will be shifted out to the address inputs. The value stored in RAM address 2 will flow out to the MUX, and since the opcode LSB is 1, the MUX will output this value to the ALU. Since the ALU's function is B, this value will pass right through and be stored in the accumulator. The next instruction is add 1. Since the MUX will be low, the constant 1 will flow right through to the ALU B input. The ALU function will be A plus B, and since A is the already obtained value from the accumulator output, which is the value stored in address 2 of RAM, 1 will be added to whatever was stored there, which we can assume was 0 since the program just begun. This value is then stored back into the accumulator. On the next instruction, store to 2, the value stored in the accumulator will go to the RAM inputs, as the constant 2 will flow to the address input, and the read-write bit will go low on the RAM, enabling a write on the next clock cycle. The last instruction is go to 0, where you want to go back to line 0 of the PC counter. Since the ALU function is simply 1, the A equals B pin will go high. Since the PC bit is also high, this NAND gate will go low, and because the load feature on the PC is active low, the value 0 will be loaded into the program counter, which creates an infinite loop. Lastly, here's a slowed down demonstration of my addition to the project, which uses persistence of vision to display the numbers. Here's an animated representation of this working, where it takes the opcode output and plugs it directly into this EEPROM.